Hi everyone, my name is Bill Burns. I'm the product manager for TotalView. And today I wanted to talk about one of the new features that was released in our 2025.1 release, and that is the ability to debug both agent and wave level threads with TotalView. TotalView debugs code that both runs on CPUs and GPUs, and in both cases there's execution control that the debugger can use to control how your program progresses through the lines of code, and also different control models of how you control the threads and access data and so forth. Debuggers use different system capabilities and frameworks for this execution control, and there's different workflows that are built on top of these capabilities. When debugging at the CPU level, you can control an entire process and examine program data, but you can also go down to the thread level and look at individual threads, examine the data for those threads, and control the execution of those threads. Libraries such as OpenMP facilitate how debuggers access these threads and information about the relationships between the threads. On GPUs, the execution and control can differ depending on if you're debugging NVIDIA or AMD GPUs. In NVIDIA GPUs, debuggers control the execution at an entire device level. So when you run code, you're running the entire device, and when you halt code and step code, you're stepping all the threads which are encapsulated through waves and lanes and so forth across that device. The debugger represents this through a thread, but that thread really has many threads underneath it. In AMD GPUs, there's two levels of execution control. You can debug at an agent level, similar to NVIDIA GPUs, where you bind the debugger thread to the entire GPU and all the code that runs on it. In this mode, it's very performant and scalable because you're working at that agent level, not down to individual threads and having to track all of that. You can switch to a wave thread mode, and in that case there, the debugger is binding the debugger thread to GPU waves. Now, you may have thousands of waves running on a device, but this does give you more granular control. Through those waves, you can move those waves and the threads within the wave and look at data of those wave threads as well. Now, as part of, like I said, the 2025.1 release, we've added this ability to TotalView that you can toggle between an agent or wave thread mode. This can be done on the fly, just by selecting a menu item and switching from the default of agent mode and then going into wave thread mode. And once you move to a wave thread mode, then you can use commands down such as stepping or to run or to next at the individual waves. So what does the interface look like when you're switching between these modes? On the left is agent mode. This is the default mode when you start debugging on an AMD GPU. When you stop in code, you're going to see in our process and thread view the representation of that agent thread. In this case here, 1.-1 is representing all the code running on the GPU and all of the threads underneath that. If you toggle to wave thread mode, you will now see the individual wave threads, and they're similarly represented by the process ID first and then the thread ID as a negative number second. So in this case here, when we toggled, we expanded to show the 4 wave threads that are running on this GPU. TotalView is a parallel debugger, so when you execute commands, whether you want to run, step, or next, you can target where that command is going to. So by default, TotalView gives you 2 groups, a control group and a share group. The control group is the entire parallel job, including the starter process. A share group is all processes that share an image. You can also target to just the process in focus, or even down to the thread in focus. These concepts of when you are working across of processes and threads are similar in a CPU or GPU. So developers are probably familiar with targeting down to a CPU thread and stepping only that thread. Now you can do the same with wave threads on AMD GPUs. You can also navigate across the code that's running on a GPU using the GPU focus controls. So these are some toolbars that appear when you start debugging on a GPU. And you can look at a GPU in a logical sense, where you're looking at the work groups and the work items, or in a physical sense, where you look at the agents, the queues, dispatch, waves, and lanes. These examples here are specific to the AMD GPUs and how they represent the code that's running on a GPU. NVIDIA GPUs are similar. They have their own GPU-focused controls as well. When you set breakpoints, you can also control what that breakpoint does when it's hit. So you can stop either the entire group of processes that are running when they hit that breakpoint, or the process itself, or even down to a thread. So if you are debugging an AMD wave thread and you specify that when that thread is hit, only that thread will stop. The other wave threads will continue running. It's a very similar concept to when debugging threads on a CPU. If you're creating an evaluation point, we have directives in there such as a $stop thread, so that when that is hit, that directive is hit and that instruction is given, that thread will stop as well. And this applies just the same to the wave threads as to a CPU thread. When you're examining data and you're looking at thread data, you can look at that through our data view and even graph it through our array view as well. So let's take a look at a debugging session, and we'll see how this all comes together. So I'm going to start a program. We're looking at main here. This is CPU code. And I'm going to set a breakpoint in this code so that when we're done processing a matrix multiplication, we're going to examine that matrix at the end. Let's scroll up into the kernel code that will run on an AMD GPU. And that's going to be executed through matml kernel. All the breakpoints are not darkened at this point because I haven't started running the code. So when I set a breakpoint, we show a hollow marker. When this code gets loaded on GPU, we'll be able to satisfy that breakpoint location and fill that marker in to be solid. We'll set another breakpoint later in this routine, and we're going to examine some thread level data when we get near the end of the routine. On the left, we have our process and threads view. And now we're going to go up and actually run the whole process, and we'll see the process and the threads come into that view. And the agent GPU thread, we start in agent mode, shows as 1.-1. All of the code in this GPU is now stopped at our breakpoint at line 109. We can also go down to the CPU code and by double-clicking focus on 1.1 and examine where we are in the call stack. So we can go down through and look at the matml call, and it's just after it's sitting at line 83 waiting to return from this GPU code. And we can go up the stack to see where that was actually called from our main routine. So let's switch to wave thread mode by simply toggling the menu. So now on our process and thread view, if we scroll down, we'll see the 4 wave threads. So instead of just 1 before, now we have 4 wave threads running here. I can double click on them to see where they are. They're all stopped at line 109 at our breakpoint. So let's change our control now down to thread level, and we're going to now operate at 1 wave thread at a time. Here's the GPU controls in our toolbar, and as we change some focus between these threads, we'll see the waves change on the physical sense or the work group change in a logical sense. You can also change the controls there yourself in the by the spin boxes and change the focus as well. So let's step this one thread, this one wave thread, and we'll see that we now move down to line 111 and 113, and we can see where that thread 1.-4 is. We focus again on 1.-3, it's at line 109. We can step that thread now and move it down to a new line location. So we're asynchronously controlling each of these wave threads. To tell one of these threads where to go in a location and running, you can select line 125 and say run to. So now thread 1.-3 runs down to line 125. All the others are stopped at the lines they were at before. So we want to run down to the routine at the end. We're going to select the entire process and hit go. We've hit our breakpoint at line 109 because we're in a loop. Let's disable that. And now get through this loop, and we'll stop at our breakpoint at the end of the routine here. We're going to examine some thread level data at this point. So we've got a portion of our matrix multiplied in C sub. And we're going to expand that. This is a 2 by 2 array, but all we have is a float pointer here. So we're going to dive on that. We're going to cast that to an array. So we'll change that to a 2 by 2. Expand that, and we'll dive on it again just to look at it as a pure simple array. And now we can see the array data. Let's focus on another thread, and we'll do the same. So in this case here, we're going to look at this wave thread again, look at its C sub and its local thread data. We'll dive on the pointer and cast it to a 2 by 2 again. And we'll get into the array portion of it and look at the data. Okay. So we can look at the data here through our array view. So I'm going to say add to array view. We perform some statistics on the array. We can look at a histogram plot, line plot, or surface plot. Let's look at the align data, and we can see what that data looks like. And now let's do the same for our other data, and we can see that it's different. So these are their own unique data relative to each of the wave threads. Let's run our program again. We want to get to the end and look at the overall result of multiplying the matrices. So we'll disable this final breakpoint so we can get beyond it. And we'll run, and we'll hit that breakpoint at the end of main. So we are back in CPU code now. Everything's been copied back over to the CPU side. We're going to add matrix C to our data view. Let's clean things up by deleting the old data. And we're going to go through the same steps in here. Now we're a 4 by 4 array, so we're going to dive into the float pointer, cast it to a 4 by 4 array. And we will look at the individual data on that down at the array, and we can see all of everything together. And we can add that to the array view just like we did before. And that's our final result of multiplying the matrices together. We'll resume the program so it exits out at the end. So this was a quick demonstration of debugging AMD agent and wave threads, a fantastic new feature as part of TotalView 2025.1. This builds on all the functionality that we have had with support of AMD GPUs. To learn more about TotalView, you can go out to our website at perforce.com and go into the products area and find TotalView, or just go to /products/TotalView. If you are new to TotalView, you can try TotalView for free. Click on the Try Free button and try out this new capability and all the other powerful features that TotalView offers for complex programs and parallel debugging. Thank you.